This abstract map represents a continuous spatial variable, y of s, observed at distinct points across a bounded study region. Classical geostatistics typically estimates the parameters of this model using a combination of the method of moments and least squares. While these methods are simple and avoid strict distributional assumptions, they do not possess the optimality properties found in likelihood-based approaches. Unlike the likelihood framework, these classical estimation techniques are not guaranteed to reach the highest possible statistical efficiency for the model parameters. Likelihood-based approaches offer a more rigorous alternative. By adhering to the likelihood principle, these methods can achieve optimal properties. However, these methods require us to assume the data forms a Gaussian random field, meaning that every finite-dimensional distribution of the process is multivariate normal. Committing to this likelihood framework secures statistical optimality, but it forces us to solve two specific problems: mathematical bias and a massive computational bottleneck. In a spatial dataset, we use maximum likelihood estimation to determine both the mean function and the spatial covariance parameters. The first roadblock is that standard maximum likelihood estimators are biased when calculating spatial covariance parameters, like the CIL and range. The second roadblock is the sheer computational cost of the likelihood function itself. The math becomes overwhelmingly heavy. This is the covariance matrix, sigma of theta. We must calculate its determinant and inverse. Because spatial data assumes correlation between all points, the matrix is dense. This inversion is an O to the n cubed operation. As data grows, the workload increases cubically, outstripping available processing power. To use likelihood methods on modern datasets, we have to engineer a way around this parameter bias and the cubic scaling of the matrix calculations. We begin with the foundational spatial linear model. Here, the variable y of s is the sum of the fixed effects, beta, and a zero-mean Gaussian error process, e of s. While beta represents the parameters for our observable covariance, theta represents the covariance parameters that govern the error process. In standard maximum likelihood, we eliminate beta from the problem by substituting it with its generalized least squares estimator. This is called profiling. It results in the profile log likelihood function, which allows us to focus entirely on estimating the covariance parameters, theta. The flaw in this approach is that it treats the mean as if it were known exactly, rather than estimated from the same data. This leads to a loss of degrees of freedom. We are using the data to estimate both the mean and the covariance at the same time. This loss is particularly severe in spatial statistics because the data points are not independent. The correlations between points mean they provide overlapping information. Because the profile likelihood doesn't account for this, it creates a false sense of precision, causing the model to systematically underestimate the true spatial covariance. The solution to this bias is restricted maximum likelihood, or REML. REML avoids bias by maximizing the likelihood of n-p linearly independent error contrasts, rather than the raw observations. An error contrast is a linear combination of the data, designed to have an expectation of 0 regardless of the values of the mean parameters. Using this projection matrix, we collapse the data vector orthogonally into a space that consists only of these error contrasts. This projection filters out the mean trend entirely, leaving behind only the correlated spatial residuals. The resulting restricted log likelihood includes this extra penalty term. This term mathematically corrects for the uncertainty of estimating the mean, which eliminates the bias found in standard maximum likelihood. However, there is a trade-off. While REML reduces bias, it can increase the variance of our estimates if the spatial dependence is very strong. REML protects the covariance estimate from bias, but it doesn't solve the computational problem. We still have to deal with that cubic matrix inversion. Even with REML, we are still required to calculate the determinant and inverse of the covariance matrix. In an O of n cubed environment, simply doubling your number of observations doesn't just double your work, it exponentially multiplies it by 8. For large-scale spatial data, calculating the exact likelihood is impossible. We have to use structural approximations to the matrix itself. One strategy is covariance tapering. We introduce a tapering function, CT, which drops to 0 beyond a threshold, gamma. By taking the element-wise Shor product of our true matrix and this function, we force distant correlations to 0, creating a sparse matrix. Sparse matrices are significantly faster to process. By forcing these zeros, we reduce the computational complexity and bypass the cubic bottleneck, making large datasets manageable. Tapering relies on the fact that very distant points have negligible influence on one another, allowing us to save resources while keeping the local signal intact. Another strategy is Vecchia's approximation, which focuses on probability rules rather than the matrix structure. We can express the joint probability of a dataset as a sequence of conditional probabilities. In an exact likelihood, predicting one point requires us to condition it on every single previous point in the entire dataset. Vecchia's approach truncates these connections. It conditions each point only on a small subset, Q, of its nearest neighbors. This dramatically reduces the size of the matrices we have to invert, cutting the required compute time. Composite likelihood methods take a similar path, often analyzing only pairwise differences between observations to avoid the full matrix altogether. These methods, like tapering, using Vecchia subsets, and composite likelihoods, all trade a small amount of statistical efficiency to make the computation possible. Analyzing massive spatial fields requires solving two fundamental problems at the exact same time, using REML to eliminate parameter bias, and deploying strategic approximations to keep the computational cost within the limits of our modern hardware.